No, it doesn't work. It is not working. I will, no, we try again. Does it work?
Yeah,
okay, fine, thanks a lot. So I would like to thank the organizing committee and Alfredo for inviting me to give a talk here. And in this, most of the material of these talks comes from research with some colleagues and friends. Gianmarco Gurioli and Benedetta Morini from the University of Florence, Natasha Craig and Natasha Clerc-Jerinchik from the University of Novi Sad, and Philippe Touant from the University of Namur, and I would like to thank all of them. So my talk is about second-order methods with approximation in derivatives. And I will mainly focus on dynamic approximation of the Hessian and on inexact Newton method and cubic regularization method. So these are the two methods that I will discuss. And the motivation for this problem comes from the solution of finite sum problems. And so I will start from the introduction of to these problems. And then I will give some conclusion. So this is our general unconstrained optimization problems that can be non-convex. We look for first order, for epsilon g approximate first order optimality point. So we require that the norm of the gradient at the point that we are looking for is smaller than epsilon g. And we focus on problems where the evaluation of f and its derivatives is expensive. And the motivation comes from the solution of these problems that we have already seen in Natasha Craig's talk yesterday. And we have to minimize a function that is the average of big N function phi I. We assume that they are twice continuously differentiable, and big N is large. So if big N is large, the computation of this function is expensive, and it is the same for the derivatives. And these problems comes from machine learning, where we have a training set that is given by big N, the capital N examples, and so capital N is generally large. And in this example, we have the AI that are the feature that belongs to R small n, and bi that are the label. And phi I is the loss function associated to the feature AI. And this is the so-called empirical risk. And we would like to minimize this one in order to find the unknown here. The x is the parameter of the model. And we would like to minimize this in order to be able, with the model, to predict data AI that, for which we do not know the label. So we focused on binary classification problems. Not we focused, but the problems that I will show you, the numerical results, are on binary classification problems. And we consider both the convex formulation and unconvex formulation. If we use the logistic loss, we end up with a problem of this form. And the x here are the parameter of the model. It is generally regularized by this term. So at the end, we have a strongly convex problems. On the other hand, if we use the square loss as a phi I function, and here we have the sigmoid as a model, as a prediction model, we have an unconvex problems. And once we have computed the x, so we have solved the minimization problem, if we have a new instance AI, we classify the instance in this way, depending on the value of the sigmoid, if it is greater or smaller than 0.5. So since the evaluation of the function and the gradient is expensive, it is common in this area to approximate this terms by subsampling. That means that we fix a sample size m, and we generate a sample set that is a subsample of the indices that goes from 1 to n of cardinality m. We generate this set picking up these indices randomly and with uniform distribution, and we approximate the function as the average of the phi I over the set IM with the indices that are in IM. So this is less expensive to evaluate than the full function. And we can do the same with the derivatives. Obviously, the sample set, it is not necessary that it's the same. It is just to simplify the situation. And we can also take m equal to 1. And in this case, if we consider a first order method, we end up with the stochastic gradient method. And the reason for considering these small samples is not only for saving in computational cost, but also because it is well known that in the data set, in the training set, there is some redundancy, and so we can use less examples, at least at the beginning of the process. Now, there are different strategies for choosing the sample size. The simple one is to choose a fixed fraction of the samples for all the optimization procedure, but this is very often done by trial and error because it is really problem dependent. There are heuristic strategies where the sample size is increased with some rules. That is, for example, that is increased by a certain percentage at each iteration. So at the end, it ends up with the full sample. And more elaborate schemes where there is a dynamic choice of the accuracy that we want on the function, the gradient, and the Hessian. And the sample size is chosen so as to have this accuracy with some probability. So here, for example, F is the accuracy that we would like to have, and we choose M in order to have this accuracy with the probability that is at least 1 minus PF. And we can do this because there is an important result that say us that we can have this accuracy with this probability if we choose the sample size larger than this quantity or this one. And you can see that here we have the probability within the logarithm. So the probability has not a great impact on the size of the sample. But we have the accuracy here squared at the denominator. And this is what influences a lot the sample size that has to, according to this rule, has to be of the order of 1 over the accuracy squared. And at the numerator here, we can have the variance of the function realization or a bound on the value of the function. And we can do the same with the derivatives. It is the same. So in very recently years, there was a huge interest in second-order methods with approximation of the Hessian, the gradient, and I listed here and in the next slides the paper I'm aware of. But you can see that most of them appeared in archive just in the current year, so maybe I forget someone, and I apologize for this. And you can see that we have Inexact Newton cubic regularization, trust region. We have paper that approximate only the Hessian and the gradient, all the terms, Hessian gradient function. We have also inexact restoration plus trust region or adaptive cubic method. So there is a large number of papers that appeared. There are also papers about quasi-Newton method that employed approximate gradient. And as a general comment, some of these papers are focused on the finite sum problems, so the approximation comes from the subsampling procedure. And there are some of these papers that are more general, but all of them are motivated by these applications. And not only, there are some papers that have some other motivation, but this is the main one. And there are some of these papers that do not approximate the function, but in some situations they do not use the function because they are less sophisticated, so they do not use stepsize control. And so they do not need the function, and so they can get rid of this approximation. So now I will focus on dynamics dynamic accuracy in the Hessian for these two classes of methods. And this is some notation. I will use bk as the approximation of the Hessian. Delta k is the error in the Hessian approximation, and gk is the approximation to the gradient. And now I will start with inexact Newton methods, and I will consider strongly convex problems. We can somewhere this assumption, but to make things easier, I assume that we have F strongly convex, and that the Hessian approximation are all positive definite with smallest eigenvalue that is bounded away from 0. And this is a general framework, and it's not necessarily bk and gk comes from subsampling. Then we come back to the finite sum. So in the general case, we have this is the framework of an inexact Newton method. It's quite standard. So we choose the forcing term. We use CG as a method for solving in an approximate way the linear system. This is the linear system, and this is the classical condition that it is required in inexact Newton method. So Sk has to satisfy this condition. And this is the residual in the solution of the linear system. And then we update the iterate, and if we use a line search, we have alpha k here. The only difference from the standard method is that here we have an approximated gradient, and here we have an approximated Hessian. So this is the difference. And now, if we think to use the exact gradient, the point is which is the accuracy that I have to ask to the Hessian, to the approximation of the Hessian, in order to maintain the good local properties of the Newton method with exact Hessian. So what we know from the theory of Newton method is that we can have Q linear convergence if eta k is small enough, and Q superlinear if eta k goes to 0. So we can prove that we can have the same if the error in the Hessian delta k is bounded by this term. That is, omega is a constant in 0, 1, and here we have eta k. So what we understand from here, we understand that if we have the Hessian that is approximated with rough accuracy, we don't need and we don't have to solve the linear system with tight accuracy, because it doesn't help, because we cannot reach Q superlinear convergence. We cannot only have the Q linear. So this means that even if n is not large, it is useful to use an iterative solver, because we can stop before reaching the true solution, and we can solve the linear system with the accuracy that we need. On the other hand, if we want to have a fast method, we have to increase, since eta k has to go to 0, we have to increase along the iteration the accuracy in the Hessian approximation. So we can start with a rough approximation of the Hessian, but along the iteration we have to increase it. With the same rate, we increase, we push eta k to 0. So if we come back to the finite sum problems and we think to have approximation that come by subsampling, we can approximate, as we have already said, we can approximate the gradient and the Hessian in this way. And these sets are two different sets, sampling set for gradient and Hessian. But generally, the cardinality of the set where we sample the Hessian is smaller than the cardinality of the set where we sample the gradient. That has to be more accurate than the Hessian. And we assume that the phi I are strongly convex. So we have that bk has the property that we need. So what can we prove if we have an inexact Newton method, Newton-CG method, where we have that nk increases with geometrical rate? And here we have the approximation of the gradient. For the Hessian, what we can ask, we can relax the accuracy that we have seen before, because I would like to merge this method in a line search procedure, so we can start far from the solution. So we have to require this accuracy omega eta k when we are close. But when we are far from the solution, we can relax this condition. And so here we have the maximum between eta k and the norm of the gradient. And this can be large at the beginning of the process. So we can use a rough approximation of the Hessian. And so in order to have this accuracy with some probability, we know that we have to choose the sample size in this way. So now we have a process where we have nk that is increases with geometrical rate. So at the end, eventually, we have the full sample for the gradient. And here we have a dynamic accuracy for the Hessian with the sample size that comes according to this gamma k. So if we do this one, we can prove some results in expectation. And we can prove that we recover the results that we have in the deterministic case. And for the superlinear convergence, we need a special form for eta k, for updating eta k, and pk has to go to 0. So at the end, the Hessian, if we want to have superlinear convergence, has to go to the full sample. And there are alternative choices that are not adaptive that have been proposed in these papers. In the Rusta-Corazani-Mahoney approach, they prove the Q-linear convergence in probability, and this is a fixed accuracy, so it does not change along the iterations. And here we have the same, an accuracy that does not change. It's not the accuracy, it's the sample size that is fixed along the iterations. And in these two papers by Nocedal and Bola Pragada, Bert Beras, they prove the analysis in expectation, and they provide also a complexity analysis. Now, for the global convergence, we can merge this method in a line search procedure. So what we do in this case, we approximate the function in the same sample set, using the same sample set that we have used for the gradient. So the gradient and the function are approximated using indices in the same set nk. And we use a non-monotone line search strategies. And the reason is that we are imposing a decrease in a function that is approximated. It's not exact. So it does not make sense to impose a strict decrease of the function. So here we have this non-monotone line search. We have this term Nik, that is the term that drives the non-monotonicity. And we have an important property that is this one for the step. So we can generalize the complexity analysis that has been given in this paper by Grappiglia and Sachs. We can generalize this analysis to the case where we have the function and the gradient that are approximated. And we can prove some complexity results. And we can prove that even if we are working with cheaper approximation, whenever nk is smaller than n, we can obtain the same complexity that we have in the case where we use exact function and gradient. Obviously, we have to impose something on the accuracy that we have, and this can be obtained, for example, using nk that increases at a geometrical rate, as we have already done, because the point is that at one point we reach the full sample. And there are also probabilistic complexity results in this paper by Rusta and Mahoney. So this is a different approach where they use the Armijo line search and they have the exact function. Now we'll show you some numerical results just to give you an idea of what happens when we approximate the Hessian. So I will use exact gradient and exact function because I'm focusing on the Hessian approximation. And the main point here, this is strongly convex. The main computational effort here for computing phi I is this scalar product. And once we have this scalar product, we compute the gradient of phi I, and we have the function phi I for free. So if we have to compute the gradient, the cost of the computation of the gradient is this scalar product. The function comes from free. And if we look at the Hessian, we are using CG in a matrix-free manner. So we compute the product of the Hessian times a vector. And this is the sum of the gradient of phi I times the vector. Each product here is expensive as evaluating the gradient. So we take as a measure of the computational cost the number of full gradient evaluation, and the cost of one matrix vector product is in CG is dk over n, one full gradient evaluation. Okay? And so we have a saving here because we are not using the full sample for the Hessian. So I used the adaptive choices for eta k that we have seen, and this choice for the k that comes from the rule that we know from the results that I have shown you before. So essentially, here we have the square of gamma k. That is the accuracy that we require to the Hessian. And we compare our method, where we start here with the 10% of the samples, and then we increase the sample size in an adaptive way. And it can also decrease sometimes. It depends on this rule. And here we compare with the method where we use 10 to minus 4 for eta and the 30% of samples, adaptive eta and the 30% of samples, and the full method. And the choice here of the 30% of sample it was not easy because this is really problem dependent. So there were some problems where it worked better the 30% of samples, others where it worked better the 10%. This was the percentage where we have the advantage in most of the problems that we used. And I insist that the idea of the adaptive choice of the sample size is exactly that of getting rid of this choice here that is difficult and problem dependent. So this is a typical plot that I can show you. Here we have 10 to 4 samples in the data set. And if we look to the training error along the iterations, obviously the method that uses full information is the fastest one. But if we look to the computational cost, we see that it is too slow. So it does not make sense to use the full Hessian. The adaptive method is the fastest one. Here we have the methods where we have the 30% of samples that they still work well. But the point here is that with the adaptive choice, I do not have to choose the sample size. And this is what we have on the testing set, because in these problems there is always a testing set where we test the model that we have, and we can see again that the dynamic method works well and the full method is too slow. Here this is the sample size, so you can see that sometimes we increase, then we decrease. Here this is the 10%, and at the end we end up with a full sample, because we are asking fast convergence. And this is another data set where n, the small n, is 5,000. So it just to show you that the linear algebra here works well, because now the problem is larger, the linear system that we have to solve. But since we work with an eta that is large for most of the iterations, the number of CG iteration is not high, because we are not solving the linear system with a great accuracy. Here we have small sample size in the Hessian and low accuracy in the solution of the linear system. So the linear algebra is not expensive. Now I would like to go to the cubic regularization method, but I would like to know how many, the time. Because there is not the watch there. Thanks. So in cubic regularization method, the step sk that is used to update the iterate is an approximate minimizer of the cubic model. That is the second order Taylor expansion of the function plus this cubic regularization term. Sigma k is the cubic regularization parameter. And an important property of these methods is that if the Hessian is Lipschitz and sigma k is greater than L over 2, any step that provides a reduction in the model with respect of the value of the model in 0 is such that it provides a reduction in the function. So this is quite important, and the complexity results of this method comes from here. And in the methods that I will show you, I will use the scheme, the algorithm that is given in this paper by the Brazilians and Philippe Thuan, where, because the analysis with this approach is really easier than the analysis that we have for the in the previous papers. So with this analysis, it's easier to introduce approximation in the Hessian, as we would like to do. And just to recall here that these methods have optimal complexity, and to approximate a first order point, approximate point, they need no more than epsilon g power minus 3 over 2 iterations against epsilon g power minus 2 of trust region methods. And we would like to use Hessian approximation that preserves this optimal complexity. So this is the point here. And this is the algorithm that we have in the paper by the Brazilians and Philippe Thuan. And we can see that we compute an approximate minimizer of the model, and then we use for accepting or rejecting the step this ratio, that is the ratio between the reduction in the function and the reduction in the Taylor expansion. And if we reject the step, we have to increase sigma k. So it is known that if we want to preserve the optimal complexity of these methods, the accuracy in the approximation of the Hessian has to satisfy this condition. But here we have the sk, that is the step, here in the right and here in the left. And this is an issue when we have to implement this condition, because when we have to choose BK, we don't have SK at hand, because SK is the approximate minimizer of the model, and we need BK for building the model. So we cannot implement this one. So in recent years, there were these two papers that trying to get rid of this problem. So in this paper by Kohler and Lucchi, they suggest to use this condition. So we do not have SK anymore here, but we have again SK here. This implies this one, so it's stronger than this one. But again, we cannot implement this. So what they do is that they use here the norm of the step at the previous iteration. Xu, Rusta, and Mahoney suggested to use this condition, where here we have the accuracy that we required at the gradient at termination. So this is quite strong. It's a strong condition because we require high accuracy in BK along all the iterative process. What we have done is to use a dynamic accuracy for the Hessian approximation, and this CK has this form. It is simply bound, it has simply been bound if the norm of SK is greater or equal than 1, and has this expression when the norm of SK is smaller than 1. And here we have the gradient that is available when we build BK. And with this choice, what we have a cheap approximation when the norm of the step is greater than 1, and we reach CK equal to epsilon g only when we are at optimality. So we have a dynamic accuracy that increases along the iteration. The point here is that, again, we have SK here. So we have to work on this, because otherwise it's not implementable. And what we do is a sort of predictor-corrector procedure. So this is what we do. This is the algorithm that we had seen before, and the part in blue are the new one. And so we start at iteration k with a prediction of the accuracy that comes from the previous iteration. Then we compute BK satisfying this accuracy. We compute the approximate minimizer of the model. Then we have to check if the prediction was correct or not. So we have the norm of the step. And the point is here, if the norm of the step is smaller than 1, and CK is equal to C, and C is greater than this expression in red, since that the prediction was wrong, because when the norm of S is smaller than 1, we have this condition has to be satisfied. So in this situation, we reject the step. We have an unsuccessful iteration. We change the accuracy, and we come back to step 1. The important point here is that this is not a loop, because if I fail here, I go back at step 1 with this new accuracy, and now I'm sure that at the subsequent iteration, things work well, because this condition is good both in case the norm of SK is smaller than 1 and in the other case. So we have just one failure here between two successful iterations with respect to this step. And then we go on as in the classical method. The only difference here is that we have to add the prediction for the accuracy for the next iteration that is done using the current step. So it's quite easy here. And we can prove that with this approach, we can preserve the optimal complexity results of the cubic regularization method. And we can also prove that we can have these complexity results with probability, in high probability, if we are in the situation where we are not able to guarantee that BK satisfy the accuracy in a deterministic way, but we can only say that the accuracy is satisfied with some probability. And I just want to remark that if decay is larger than this term, we know that this is true, and we have this optimal complexity in probability. If we use a fixed fraction of n, that is something that is very often done, we have suboptimal complexity results. So the method works, but it is just that we do not have the optimal complexity results of the cubic regularization method. Now, I show you some results, and here we have this problem that is non-convex. And for the computation of the approximate minimizer of the model, we use Barzilai-Borwein method. And the cost of each iteration is a big K vector product at each iteration. So we are in the same situation where we were with the inexact Newton method for the computational cost. And this is the data set that we have already seen before. And we compare our method with the cubic method with the prefixed function of the samples and the full method. And again, also in this case, we can see that we don't have to use the full method because it's too expensive. And here, the dynamic approach works well. But if we look to what happens for the fixed fraction of samples, we can see that if we use the 1% of samples, the method is too slow, is too expensive because it's too slow at the end. So even if the Hessian is approximated in a cheap way, at the end you end up with an expensive method. So this is too small. And for these three sample sizes, they work well, and it's not easy to say which is better from this one. So we can also work with fixed sample sizes and paying attention to the way we choose them. And this is the same for the training loss. Now, if I have time, 10 minutes to 50. No, so too much. OK, I will not show you this one. This is a different approach where we can work with function, gradient, and Hessian approximation. And so in this situation, we approximate also the function and the gradient, and we lose something in complexity, but I do not have time to show you this one. I would like just to point out something about the comparison between first and second order methods, because in this field, in the machine learning community, most of people use first order methods and thinks that second order methods are not useful. And it is not easy to assess at this point. You can see that these are all papers that report computational results. And there are these papers where it is shown that for some problems, ill-conditional problems, second order methods are useful. They are less sensitive to parameter tuning, and they can also be implemented in order to converge to second order optimality point. There is this paper by Adolf Kohler and Lucchi that in deep learning show that there is a marginal contribution of second order information, so exactly the opposite. And I would like just only show you one experience that we had, and this is a data set that comes from a real-life application. It comes from a collaboration that we have with some engineering, and it is a parameter design of centrifugal pumps. And this is the training set size, and it is an unbalanced data set. So we have to training the model in order to classify if a pump is feasible or unfeasible. And in the data set, we have a large number of infeasible pumps, larger than the one that we have for the feasible. So it is unbalanced. And we compared the method, the cubic regularization method with Hessian approximation, with some first-order methods that are widely used in the community, and also with this method that is a method where we increase the accuracy in the gradient. We have also used the full gradient method, and we end up always in this situation where this is the testing loss. And you can see that with the second order method, we can reach smaller values of the testing loss than the values that we are able to reach with the first order method. And if we use the first order method, we are not able to classify correctly the positive labels in the testing set. So it doesn't work. And the point here is that the second order information gives the possibility to reach this value of the testing loss. Because even with the full gradient, we end up here. And with our method, so after training with the cubic regularization method, we have an accuracy in the binary classification that is the 89%. So in this situation, for example, the second order methods are needed. So just some conclusion, and as you have seen, there is a great interest in second order methods with inexact derivatives informations. I think that the sample size that are provided by these rules that comes from matrix concentration inequalities are too pessimistic. So maybe it is needed to work on this, because if the set is not too large, we end up too early to the full sample. And it is not needed in practice. So this means that the bounds are pessimistic. Obviously, it is needed further investigation on first order versus second order methods. And since the dynamic accuracy in the Hessian provided a more robust method and less sensitive to parameter tuning, dynamic accuracy in function and gradient in the same flavor should bring benefit, but there are just a few works in these fields so far, so we should improve here. And thanks for your attention, and happy birthday.